Hi guys, it's Saturday, February 2nd. I'm really sorry I haven't made a video in a really long time, and so to make up for that fact, today I'm going to try and explain Einstein's theory of special relativity. Obviously, I'm not going to really be able to explain the whole thing within the amount of time that I have to make a video, because that would be super long and really boring, but my hope is that I can explain it well enough that you will sound smart at your family gatherings and everyone will be really impressed that you know about the special theory of relativity and physics and stuff like that. And also, I just think it's really interesting, so hopefully you will too. A lot of the ideas that I'm going to talk about I've been thinking about recently because I am reading this. It's The Elegant Universe by Brian Greene, which is actually a book that is about string theory mostly, but it starts off explaining Einstein's theory of relativity, both general and special, and then it goes into quantum mechanics and then goes into that. I'm reading it for a class that I'm taking that's a seminar, but Brian Greene does a really good job explaining everything in kind of simple terms, and so I'm going to kind of steal some of his examples to try and help you guys explain, so like no copyright infringement intended or anything. So one of the basic ideas underlying the special theory of relativity is that the speed of light is a universal constant. Nothing in the universe can go faster than the speed of light. Think, well, you know, if you get something going close to the speed of light, why not just push it a little bit faster? But special relativity explains why that is not possible. So something that's interesting about when you're moving close to what we call relativistic speeds, which is really fast, gets close to the speed of light, it affects not just how fast you're moving, but how fast time is passing for you and the length that objects seem to be. To kind of make it more feasible, something you can wrap your brain around, imagine you are traveling in a car. And you know when you look outside and you look at the trees next to you on the freeway, it looks like they're moving. Relative to your position in the car where you're holding still, the trees next to you are going at 60 miles per hour, or however fast you're driving. If you were to be traveling at relativistic speeds, relative to you, everything else around you is moving, not you. But to somebody outside of your frame of reference, it would look like you were moving really fast. And so that's where the whole term relative comes from. So to someone outside of your frame of reference, when you are moving at relativistic speeds, time passes faster for them than it does for you. There's actual experimental proof of this. People have done experiments where you have atomic clocks, which are super accurate timekeeping devices, and if you leave one on the ground and you put another one in a jet plane and fly it as fast as you can for a long amount of time, when you get them both back together, the time that has passed for the clock that stayed on the ground is longer than the one that was in the airplane. That is called time dilation, the effect of time due to your speed. The effect of length due to speed is called the Lorentz contraction. Again, it's not really something that you can see in everyday life because you're not ever going fast enough, but the idea is that if you were going fast, again, an outside observer would see you as being compressed. You'd be shorter width-wise than you would in real life. Now, the reason that you can't exceed the speed of light is because it's a sort of energy cap. Another kind of example to think about this with is if you're in a car, and let's say the maximum speed the car can go is 100 miles per hour, and there's only two directions you can go. You can either go forward, or you can go left and right. If you travel forward for a certain amount of time, let's say 50 seconds, why 50 seconds? Make it 60, make it a minute. Okay, so if you travel at 100 miles per hour for a minute in a perfectly straight line, you will get a certain distance. But if you travel at 100 miles per hour in not a perfectly straight line, where some of your motion is also used to go to the right, say, you won't get as far in the same amount of time, because some of your energy was put towards moving forward and some of your energy was put towards moving sideways. It's the same kind of thing with going through space and time. Even though we, in our everyday today life, only experience movement through the third dimension, we're also moving through time. We move through space and we move through time at the same time. This gets hard to talk about. So the idea is that the speed of light is like our speed limit. Where our car could only travel 100 miles per hour, we can only use the amount of energy that light travels with. So usually we cannot get close to the speed of light because we are moving through both space and time. So some of that energy gets used to go in both directions. And that's where the idea of space-time as being one combined entity comes from. And I know I've completely butchered this idea, but hopefully you kind of have a little bit more of an idea about when someone mentions, oh, Einstein's theory of special relativity, you can be like, I know what that means. It basically just means the world is crazy and insane and time isn't real, essentially. So hopefully you found that at least a little bit interesting and hopefully made some sort of sense. I'm going to have to see when I'm editing if I need to add anything else in to make that coherent. But yeah, yay science! Claire, I will see you on Monday. The sun is the